Hello again. So there was some problem with my computer. My last video, which contains the problem sets that help you understanding the differentiations topic, I uploaded, but there was no audio, unfortunately. And at the end, I wanted to cover 25, but my computer was shut it down. So therefore, in this video, I'm gonna explain a little bit more on the problem 25 because I think it is quite important because this is the proof of new Newton's method. Okay, so again, let's read the problem together. So f is twice differentiable on the closed interval AB, and we have the rule that f a is smaller than 0, f b is larger than 0, and f prime of x is strictly larger than 0, right? So that's the definition for this, the existence of such delta. And we also have f double prime is smaller than m for all x in AB. So this basically means the second derivative is upper bounded by m. Okay, and let C be the unique point in AB at which, so C is the unique zero of function f, and C is a point that in between the interval AB. And we want to show, first of all, choose x1 in these intervals, and we want to interpret it geometrically. So it is, once you draw the graph, it becomes pretty easy to understand. So notice that this angle, right? This angle is actually equal to, so the tangent of this alpha is equal to this divided by this, right? So at the point, so f prime of x is equal to tangent alpha. And then because tangent alpha is equal to f1 divided by this distance, so this distance is actually equal to this divided by tangent alpha, where tangent alpha is equal to f prime of x. So that is the geometric understanding. And I think the main challenging part is part 2 or part B. So let's show that xn plus 1 is smaller than xn, and that the limit converges to epsilon c. So to show this, whenever you encounter some statement about like a sequence, I think it's a good idea to examine if you need to use induction, because I wouldn't think about that, so that spent me a lot of time. But if you, and then, okay, I look at the hand, and then it's actually pretty natural to think about using the method of induction. So let's just prove x2 is smaller than x1. And notice that this is our interval AB, this is C, this is x1, and we know that f0 is equal to 0 at C, and we also know that f prime of x is strictly larger than 0, which means our function f is actually monotonic, strictly monotonic increasing. Therefore, fx1 is strictly larger than 0. And as I write down here, we have by the mean value theorem on evaluating on this interval, we have this inequality. So there exists the P in this interval, C x1, such that this equality holds. And then because P is less than x1, so we have this inequality. And then by this inequality, we have this, and do some algebra, we can see this is exactly the definition for x2, and therefore we're done. And we need to do it for n. So suppose we have xn that is larger than, so our claim is actually we're not directly tackle on xn plus 1 smaller than xn, but we're actually tackle on xn is larger than xc for every n. So the induction step is to assume that for some n larger or equal than 0, such xn is larger or equal than xc, right? So we prove that, and then we use the mean value theorem on the interval xc, comma xn, and then to obtain this inequality. And once we do some algebra, again, we are using the fact that f prime is Let's wait a second. Oh, actually, another information we have. So here, this is um, larger than f prime of p, given that the p is smaller than x1. This holds because we know that f double prime is larger or equal than 0. Therefore, f prime is a monotone increasing function. Therefore, we have this is larger than this. Okay, and then we keep using that, and then we have this. And therefore, for all n, we have x is larger than c. And then recall that our ultimate goal is to show that, notice that our ultimate goal is to show xn is xn plus 1 is smaller than xn, right? And then I think for that we can show xn plus 1 minus, or we can show xn minus xn plus 1 is going to be large or equal than 0. And to show that, what we can do is we just need to show this, right? Apply the definition for xn plus 1. So we need to show this is strictly large than 0. Well, we already know f prime is larger or equal than 0. So we only need to show this is larger or equal than 0. But we know that for every xn is larger than c, and c is the unique 0 for. So everything on the right hand side of c is going to be strictly positive. Therefore, the whole thing is positive. Therefore, xn is larger than xn plus 1 for every n. And we prove the first part of this part B. And to show the limit of this, I think it's another tricky thing, and it took me some time. So we want to show the limit of xn converges to c, and I think first of all, we have observation that xn is a decreasing sequence, and it is bounded below by c. Therefore, it's convergent, and therefore, because it is convergent, we have that because it is convergent, we do have the fact that it is a Cauchy sequence. Therefore, xn minus xn plus 1 converges to 0, xn converges to infinity. And why do I want to use that? Because xn minus xn plus 1 is equal to fxn here over f prime xn. And we know this converges to 0. And there is a fact that, well, because our second derivative of f is bounded by m, is strictly and bounded m larger or equal than 0, we actually know that this one, well, never mind. I think because this is large or equal than epsilon, so this one is actually smaller or equal than fxn over delta. So we have this, right? And then we have this is a constant, and we know because of this is converges to 0, this converges to 0, and therefore we know this converges to 0, and that implies the only possibility is fxn converges to 0. And because fxn converges to 0, how that will help us to prove the limit of xn converges to epsilon. Okay, so we're almost done. We have fxn converges to 0, but we also know that xn is a convergent sequence, so it must converge, and f is continuous, right? So using the sequence definition for continuity as xn converges to, so we assume xn converges to c1, which is strictly larger than c, because we want to reach a contradiction. So as xn converges to c, fxn should converges to f c1, right? But fc1 is equal to 0 because we just proved fx1 converges to 0. However, we call that c the unique 0, and everything on the right hand side of c should be the evaluation of f at that point on the right side of c should be strictly larger than 0. Therefore, we reach a contradiction. And then because we reach a contradiction, therefore C is equal to C1, and then we're done. And for this, for part 3, we want to use Taylor's theorem to show this. And again, it's similar as the previous problem. You look at the problem statement and you figure out the hint, and you use the hint, apply the Taylor's theorem formula, and usually it will usually it's not complicated once you observe the hint. So here the hint is like for some t in this interval. So you will know immediately that this represents alpha, your first thought, right? Okay, this is a beta and this is x in as stated in the original Taylor theorem in Rudin's textbook. But I was trying to do that first, but I got stuck because I didn't get quite exactly the same expression as the problem asked me to do. So what I tried next actually is to like this equal to alpha, this is equal to beta, and reverse it. And this is still x. And that gives me what I want. And after that, I realized that we can use Taylor's theorem like alpha and beta, because what's really about Taylor's theorem is that you have for example, we have a function defined on the real line, right? And then you have a point alpha, and then what you're doing is you're approximating a function in the center of alpha, and the radius is actually beta minus alpha. So you are actually, how to say that? So you are actually expanding your polynomial in the center of alpha, and then the edge of your expansion is at beta. So if you reverse the role of alpha and beta, so here we have alpha and beta, so beta minus alpha, right? But the way you reverse is nothing but beta is here, and you're kind of doing this way. And I think both works, just depend on which you want at the end. So for example, here at my C, what did I get is right here, I plug in, because C is my beta, so this is my beta, and this X is my alpha, and this is my alpha, and this is the Tn, and this is the beta minus alpha, and at the end we obtain the exactly same thing. Beta alpha. Okay. And then for part D, let's see what is part D. So if A is equal to this, deduce that. So again, this is a statement about a sequence N, and your first intuition should be using the induction. So for base case, when N is equal to 1, we're trying to show that x2 minus, because C is smaller or equal than this, right? Where N is equal to 1 just. And this should be pretty straightforward. Yes, you can use the fact this inequality and the fact that x double prime n is upper bounded by m, and this is upper bounded by is lower bounded by delta, so the whole thing is upper bounded by m over 2 times delta. And then once you prove the base case, you can assume using the induction step to prove it is true for n. And notice that here, I spent a lot of time and unnecessary time to show this is actually 2 to the power of n instead of 2 times n. So just be careful. And then once we did this, show that Newton's balance amounts to find a fixed point of function g defined by this. Well, this is exactly this. And by the definition of fixed point of the function, this is exactly what we're trying to do. And together with the limit x1 converges to the c. And then we want to, and then how does g prime behave for x near the c? Well, you can so the first intuition, the first step is you to compute G prime, right? Using the division rule that we proved in the first video. And then that will give you something that you can interpret further about the behavior of G prime. So for example, G prime, let's see. Yes, G prime is equal to this, right? Okay, and then let's interpret each one of them. So we know this. Well, you can, yes, this is equal to this, and you can separate them. And then because this is equal to 1, so this is equal to 0, and you only need to focus on this. And the question is, what is the limit of fx times f double prime x over x prime x squared? Well, when x converges to c, right? So, well, when x converges to c, fx converges to 0 because f is continuous, right? So therefore the whole thing becomes 0. And then we answer the question. And then for f, notice that for this function, it actually doesn't satisfy the conditions of our problem. Why? Because notice that the second derivative should be strictly larger than 0, but on like 0 to positive infinity, this part, the second derivative actually is less than 0. Therefore, when you try to use the method, the approximation method, you are actually not only oscillating, but you're far, far, far away from the 0 point, which is because it's equal to 0. So the thing is that you, for example, you fix x1, and that is fx1, and see, because it is if you are doing the same approximation, you ended up at this point, and then you can call this point x2, and then the fx2, for example, is here. Sorry, at this point, and then you do another like a secant line on that, or tangent line, you can say, and you press on this, and you can look at this, right? And it becomes just like diverse. So I can draw a big picture here. So this could be your x1, and then this x2, and then x3, x4, x5, x6. It's just become far, far, far away from the center point you could see. And that is because, so the reason that the Newton method does not work in this problem in this function, particularly because it does not satisfy our conditions. Okay, so that's it. And I hope I explained things okay, and if you find any typos or mistakes, please let me know. You can reach me just through the message, you can shoot me an email. Okay, thank you.